How many quantum particles were we talking about with this harmonic oscillator? Just one. Even if we think about simple molecules, okay, there's a couple of like noble gases. But what about like N2, H2? How many particles do they have? 2. Let's apply this to one of those systems so we can get something realistic. The interesting thing is you can do forms of spectroscopy and you can actually measure those vibrations very easily with IR spectroscopy for diatomic gases. And it lines up incredibly well with this model. But the problem is we've only looked at one. How do we look at 2? So let's check this out. Okay, what we want to do, we want to find a way to describe or model a harmonic oscillator with 2 particles in it. Or a diatomic molecule. Okay. It's not very impressive because in lab we've modeled bigger things than that. We almost never work with diatomic molecules. But we're going to learn a lot by first tackling this problem in a way to get rid of many variables. So normally, we would have a wave function that just depends on each parameter we're plugging in, right? So in this case, we would have 2 wave functions. And that makes things really complicated. We really don't want that. So how could we look at a system with 2 masses or 2 particles? So let's say we're going to first investigate this classically, and then we're going to apply it to quantum mechanics. Let's say we had 2 bodies. We'll call this guy M1 and this guy M2. And they're connected together through some form, some connection. Could be a bond for diatomic molecules. We would need equations to describe the motion of this guy, and we need equations to describe the motion of that guy. However, we can make this simpler. What did you guys do in physics when you encountered a problem like this? Or it may have been a while. Exactly. That's what we're going to do. You could use the center of mass. So let's say M1 is less than M2. Where would the center of mass be? And do you guys get what I mean by center of mass or no? Okay, so like, I don't know. I had one friend in high school who was always really obsessed with knives, like an unhealthy obsession with knives. He's coming to with Vil today to talk about stuff. He also works at Regeneron, which should be fun. But he would always balance them on his finger, and he'd like, I don't know, that was like the most important thing to him. So when we talk about the center of mass, it's where would it be balanced or at equilibrium, right? So for this system, where would you expect the center of mass to be, given that M1 is less than M2? Yeah, a little bit closer to M2. If it's way heavier, it'll be over on that side. We're going to call this displacement X1 and that guy X2. Okay. Another cool part is if you have a pure harmonic oscillator, the center of mass does not change. So even if these two go whoop, 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 if it's a pure oscillator, the center of mass will not change. Center of mass does not change. Okay. Now we could do a bunch of complicated mathematics to show how this change occurs, how it doesn't. It ends up being really tedious. Does anyone care if I just skip over that and get to the result? You do not need to know it for your Quizlet. It's basically a way to derive the reduced mass and show where the reduced mass comes from. You have probably done this in your physics class, and I just don't want to take the time to do it. Okay. The reduced mass, which I'm going to give the symbol mu. I don't know what you used in physics. Ends up becoming M1 times M2 divided by M1 plus M2 for the masses. This should be lowercase. Okay, we're considering a harmonic oscillator. Therefore, the potential energy actually, no, let's just jump right to the Schrodinger equation. Using reduced mass. We'll have the single particle harmonic oscillator and then diatomic. We showed if we were looking at the frequency of the oscillation, it was 1 over the time it took to complete that oscillation, and we derived this expression. So this is the frequency of the oscillator booping around. Tau, again, was the time it took for a complete oscillation. What's this K thing? Spring constant, or in the case of quantum particles, a force constant. It'll be used interchangeably. And then what's that M? Mass. Yep. Now, for a two-particle system, how is this thing going to change? Well, we still have some frequency. We still have some time that happens with that frequency. 1 over 2 pi, is that going to change at all? Just a collection of constants. Square root k remains the same. What's the only thing that changes? Yep, what's it change to? Yep, we change it to a reduced mass. Okay, it's really advantageous because we don't have to worry about two variables. We only need to worry about one variable relating to that reduced mass. Now, let's consider the harmonic oscillator's wave function. Negative h bar squared over, or I'm sorry, the Hamiltonian for that system. Let's do what else goes here? M partial of what? Yep. Squared plus what else do we got? Yep, 1/2 kx squared. We're just going to shorten that to potential energy operator because I'm lazy. Okay, and multiply that by psi, and we get E psi. So that's a one-particle harmonic oscillator. What's it going to look like for our diatomic pure harmonic oscillator? Yep, over 2 mu. What else? We don't even have to worry about that because we've kind of reduced it all into one parameter thanks to that thing. Potential. So now we can express a complicated system that would normally depend on two parameters with one parameter, and all we have to do is swap. Every time we have an m, we just swap in a mu, and we're good to go. So that's a pretty simplistic thing to do to make something that could be increasingly complicated way simpler. We have a reduced mass now. We just have to calculate that reduced mass to plug it in here, and everything else almost behaves the exact same. And this model works incredibly well. Like I said, you can use IR spectroscopy and UV vis spectroscopy and see that sort of stuff for different systems. Okay, let's apply it to a system. How are we doing on time? 13. Okay, this will be the last thing that we do. Okay. Example. H2 molecule vibrates at a frequency of about 0.32 times 10 to the 14th hertz. Calculate A, the force constant, the HH bond, B, the change in energy that accompanies transition from the n is equal to 1 state, n is equal to 2 vibrational level, assuming H2 is behaving as an ideal harmonic oscillator. Okay. I think it's pretty clear what we're looking for. What are the two things we're looking for? Yep, K value, force constant. What else? Yep. Tell me important stuff that we're going to need to solve this one. Yep, quantum numbers are a big one. What other things? Frequency. What other words are important in here? H2. Yep, because we're going to need masses eventually. What else? Ideal harmonic oscillator. Yep. One other big thing. Vibrational level. Okay. May not seem like it right now, but when we get to molecules, there's a difference between the energy and the vibrational energy levels of that system. All right, let's solve A first. What equation are we going to need to get to K? Yep. Pi. Yep. Over, yep, mu. Okay. We got to manipulate this around. What do we got to solve for? K. We get 2 pi that thing times mu. Does that work? Oh, wait, we need to square it all. You're right. All right, we're not going to have enough time to make it through this one. We'll get through A, and then we'll pick up on the other part. Mu, remember we got to calculate a reduced mass. How do we do that? Yep. Yep. Okay, the mass of a hydrogen atom, you can look it up. Yep, really a small number, not as small as the electron. So when you add this thing all up, you get 8.370 times 10 to the minus 28 kilograms. When you plug everything else into here, the value of K that you should get is 575 kilograms per second squared, or that's a Newton meter, whatever way you like it expressed. Next time, we'll talk about that. Yeah, we have enough time to do the energy transition, I think. B, harmonic oscillator. How did we define the energy of the harmonic oscillator? N plus what? Yep, 1/2, and what's that multiplied by? H. Yep. So we would have to calculate the difference between E1 and E2. So it would be what? 5/2 H nu minus, is that right? Yeah. 3/2 H nu, what's that going to work out to be? Yep, 1 H nu. We have nu already. We can multiply it by H. And you should get that many joules as a result. Okay, it's about all we have time for today. I do want to make mention that there are anharmonic oscillators. So if you don't have a pure oscillator, you have to look at anharmonic functions, and that becomes really taxing and difficult. We did talk about today how we can take something that is complicated, so a two-body problem, and reduce it down to a one-body problem through reduced masses. So the big thing to keep in mind when you're looking at questions on the Quizlet or on the ACS exam is to see, are you talking about a one particle or a two particle harmonic oscillator, and which way you have to go with that. Okay? We're going to use these tricks again in the future to reduce things down to make them simple.